Okay, today we will be looking at topic 10, which is multivariate data. Previously, we looked at bivariate data. So two variables, bi is two. Multi is used for more than two, so three or more. And you'll see what modifications we will need to make to the bivariate linear regression we looked at last week. I will leave this up to you all to review. Very important to see what your learning goals, outcome, assessment, and activity will be. Now we move on to multivariate linear regression. So it's still linear. So just for quick revision, the last time we looked at the equation for a straight line, which is y equals mx plus c. And we know we can write it in many different forms, right? To write it in this form using coefficients beta 1, beta 0 through to any number. Here is just going to be 2. You will write the equation in this form. So the constant term first. So it's going to be beta naught plus beta 1 x. So this is linear regression using the terms in this equation. There is only one independent or exploratory variable, and there is only one dependent or response variable. But in reality, we don't always have only two variables, meaning one exploratory and one dependent variable. We typically would have multiple independent or exploratory variables. And when you have multiple independent variables, the regression you perform is said to be multivariate. Multivariate, meaning multiple variables. So it involves multiple variables, not just two. So in this context, we use x1, x2 to represent the independent or exploratory variables. And that's what you see here. So these are your exploratory variables. And these are just the coefficients of the multivariate linear regression. Why is it linear? Because the highest order is still order 1. This is x2 raised to power 1, x1 raised to power 1, and of course this is the constant term. So the highest order here is 1, so it's linear. You're going to see on the next slide we will have other terms. This is just an example. I'm just going to call it beta k. So it's not necessarily the fourth term. And you can have x, say x1 raised to power 2. So this is going to be second order because you're raising the independent term to a power greater than 1. So it's a second order polynomial regression. Whereas these ones are all linear regression because the highest order of the independent variable is 1. So multivariate, multiple variables, linear, highest order is 1. Now we're looking at multivariate polynomial regression. So no more linear, meaning highest term can be more than order 1. So this has an order of what? The order here is 1, right? The power is 1. And that means it's a linear term. Yes, this is what I was trying to do. So these are the linear terms. But you see here, you have product of those three independent variables. So all three of them. These are all the possibilities. You could have x1 times x2. You could have x1 times x3. You could have x2 times x3. That's 1, 2, 3. And finally, you could have the product of all three. So those are all possible interaction terms. The independent variables are interacting, and their interaction still affects the dependent or response variable. And again, the coefficients still do the same thing. They basically scale the effect of those terms, including linear terms and interaction terms, on these second order terms. So these are quadratic terms because they are second order, right? Power of 2. And each of the independent variables is raised to a power of 2 here. And that's why they're called quadratic terms. And again, they also have their corresponding coefficients. How do you find these coefficients? Exactly how we found the coefficients for linear regression using least square minimization. It involves some matrix calculations, which I don't want to get into in this course because this is a course on Python, visualization, and statistics. So we're not going to go into the linear algebra needed to perform this least square, but it suffices to mention that you get the coefficients by minimizing the least square error, exactly how we talked about in the case for linear regression. Now we move on to jointly distributed random variables. Quick revision in topic 3 thereabout, when we talked about probability distribution, we looked at random variable x, right? We're trying to draw a PDF. So what's this y-axis? It's going to be the frequency. And for normal distribution, it looks pretty much like this. It's supposed to be symmetrical. And the important thing is you have only one random variable and the corresponding frequency. And that's your PDF, probability distribution function. What if you have more than one random variable and they are interdependent? Your frequency still remains on the z-axis, and now you have two possible random variables. So random variable 1 is x, and there is a second random variable y. And now when you want to draw your PDF, it's not just going to be a two-dimensional image, but it's going to be a three-dimensional image. It's a dome. So this is just, I need to clean that out. Whereas this was just a two-dimensional image, this is three-dimensional. And how does a dome look? If you've had a chance to walk around LSU, you must have seen one of these. These are the Indian molds, right? It's a dome. It's a three-dimensional image. So that's exactly what this looks like. It's a dome. And the reason is because random variables x and y are interdependent. An example of this random variable here, where it's 2D, is just like the age of students in a class. So age of LSU students, that was precisely the example I gave under this. Right now, this could be age and this could be weight. And in the example I give here, it's easy to see if you're in elementary school, the age and the weight will be correlated, right? The students in grade 6 will generally be older and also weigh more than students in grade 1, for instance. So those two variables, age and weight, are interdependent, and each member of that data set represents a point. So that's what I try to define here. When two or more random variables are associated with each item in a population, so every student in the school has an age and a weight. So each item will represent a student. So student 1 has his age and weight. Student 2 has age and weight. And that's basically what's going on here. So when two or more random variables are associated with each item in the population, the random variables are said to be jointly distributed. So the keyword is joint. Joint because you have two variables. And that's the example here. If those variables are discrete, meaning if x and y are discrete, meaning they only assume integer values. So if you took the integer value of all the ages, so there cannot be 1 point something, no decimal fractions, and the weight is also taken as an integer, then that will be a jointly discrete distribution. If it's allowed to be continuous, which is what you would expect in age, you could be 20 years and 7 months and 1 day old, it's continuous. And those variables will be said to be jointly continuous. And that's basically the difference between discrete and continuous, whether or not decimal values are allowed. Now we move on to joint and marginal PDFs. The main thing here is the difference between density function and mass function. So previously we've been using them almost interchangeably and saying PDF is whenever you have this, right? But the main difference is PDF is for continuous functions, whereas PMF, which is probability mass function, is for discrete functions. So if x and y are discrete, meaning assuming only integer values, then what you have is a joint probability mass function. Otherwise, if x and y are continuous, then what you have is the PDF, probability density function. And it's joint because you have two variables, two random variables, which are interdependent, and you can now plot the DOM for the continuous function for PDF, discrete function for PMF. Now, although they are interdependent, right? X and Y are interdependent, you could still get the probability of just X. And in that case, it's going to be referred to as a marginal probability. So the marginal PDF of X will be this kind of plot. It's PDF because we've assumed it is continuous. It will be PMF if it is discrete. So the PDF of just X by itself is probability of X. That's the marginal probability of X. Just Y by itself is the marginal probability of Y. And those joint distributions are the intersection of X and Y. So if there were these kinds of events, it's going to be this, where this is X and this is Y. That's what your joint probability is the probability of X intersection Y, which could be written in any of these two ways. So now you know what marginal probabilities are. That's Y. And you know what joint probabilities are, which is equivalent to this. So these will give you a 3D dome, right? And this will give you the same thing we've been looking at since the beginning of these course.